So then let's welcome our next speaker, Saurabh Gupta. So Professor Saurabh Gupta. So Saurabh is an assistant professor at UIUC. And before this, he was also a research scientist at Facebook AI Research. And he obtained his PhD at UC Berkeley, advised by Professor Jitendra Malik. So I know that Saurabh has a lot of interesting work on navigation. So yeah, also look forward to his interesting talk. Yeah, welcome.
Yeah, thanks a lot for the kind introduction. Can you hear me?
Yes. Mm-hmm.
Yes, okay, great. I'm going to start sharing my slides now. And you can see my slides, right?
Yeah. Mm-hmm.
Okay, fantastic. Yeah, thanks a lot for this introduction and for organizing this workshop. I really enjoyed it last time around as well, and I'm looking forward to the other talks today and such. Okay, so what I want to talk about today, the title is Learning to Move and Moving to Learn. And I like to start with this quote from Churchill and Ramchandran and Sujanowski. And this says, vision, like other sensory functions, has its evolutionary rationale rooted in improved motor control. Although organisms can, of course, see when motionless or paralyzed, the visual system of the brain has the organization, computational profile, and architecture so as to facilitate organisms thriving at feeding, fleeing, fighting, and reproduction. Right? And I guess Roosevelt talk before this talk kind of already lays the ground for this. And basically, what I'm trying to argue is that we should not view scene understanding from the point of view of just understanding what objects are where in 3D and so forth, right? Rather, we should think of scene understanding from the perspective of agents trying to act in the world, right? And Roosevelt showed you a lot about, how do you interact with the world, manipulation, and so forth. For the purpose of my talk today, at least, I'm going to only focus on a reasonably narrow definition of interaction, which is just navigating around, right? And in the first part, I will basically talk about how can we learn policies for agents to move around in the world, right? Move around in scenes, move around in novel scenes, and so forth. And I'll do this from the perspective of how can we do this with minimal active interaction with the environment. There was a lot of talk about sim to real and building simulators and so forth. And I'm going to show that how we can do it perhaps without simulation for a change, right? So that's going to be my first part of my talk. Now, if you're doing computer vision, you can't quite ignore Gibson. And Gibson said, we must perceive in order to move, but we must also move in order to perceive, right? So the second part of my talk will pay homage to Gibson, and I'll try to show that once agents can start moving in the environment around them, how they can actually move around in order to learn something about the environment. So that's kind of the overall lay of the land, and I'm going to talk about these two pieces. Okay? So let's start with learning to move. How do we learn to move? But before I tell you how do we learn to move, I think all of us should go back and think a little bit. Why do we want to learn in order to move, right? And this is, I think, a lesson for not just learning to move, asking why are we learning, but for any other problem that you're interested in. Learning is really cool. Everyone wants to do learning. There are lots of classical problems that we're injecting learning into, but one must always take a step back and think, why would learning make sense for this problem? What can you do without learning? How will that would work? And what is the right way in which learning can complement what we can already do, right? So again, for this problem of navigation, again, it's a 50-year-old field, probably more, and classical solutions are very, very good. They're very mature. They're in fact used in self-driving cars, if you will, and so forth, right? And this is, again, I won't go into the details. There is a mapping phase. You build a geometric 3D reconstruction of the world, and then you can do path planning on that and so forth, right? Now, I think in my view, why learning still makes sense for this problem of robot navigation is for this reason that learning can allow us to speculate what we don't directly observe. And this comes about in lots of different ways. For example, I may be in this particular bathroom, and I may not have been in this particular bathroom before, but I can speculate that there is this doorway, and then there is likely going to be free space on the left side outside this particular doorway, right? So you may not have been in this particular bathroom before, but you've been in enough other hotels or bathrooms or whatever before that you can very well speculate that you can exit out of this door and turn left, and there is very likely going to be free space there. You don't know for sure, but you have a very strong suspicion that that would be the case. Okay? There are other ways. There are semantic regularities, right? So here is another apartment, another house. Let's say you are visiting your friend or whatever, and you're trying to find a couch, right? Now, again, you don't see a couch over here, but a lot of you would agree that if I were to go straight and turn around this corner, I might very likely see a couch. Again, you're not absolutely sure, but you have this intuitive prediction, or you have there's commonsensical patterns in data which may not exist, but that could guide your exploration to quite some extent, right? So this is, I think, what is the role for learning in this kind of a problem. I mean, there are other reasons, but I think these are two that I like to focus on today. Okay, now I think, so if you're with me that, okay, we want to learn policies for navigation, what is the current paradigm for learning policies for navigation, right? And I think Roosbay presented a little bit of this. I mean, we can actually do policy learning via direct interaction or reinforcement learning, right? In fact, this is a picture, this is a video from AI to Thor, work that Roosbay presented. And basically, you can do reinforcement learning. It takes many, many millions, sometimes billions of samples for training, right? Now, this is good. I mean, if this is the only paradigm, then I guess we have to live with it. But this paradigm has drawbacks, right? There is impractically large sample complexity, right? So I do know policies that have been trained with billions of samples of training. Now, billions of samples, there's no question that you can just can't do this in the real world, right? So you have to build a simulation environment, right? So if you follow this paradigm, then we have to build simulation environments. Now, if you have to build simulation environments, that itself is a hard problem. You need to make sure that your simulation environments are realistic, right? You need to make sure, I mean, you can synthetically create them, or you can scan real world environments. Both, there are efforts which do both of these things, and there are drawbacks with both. If you are having artists draw them, it takes time and money. If you are scanning real environments, there are going to be artifacts and so forth. And then, of course, you have to worry about sim to real and generalization and the like, right? So the question that I'm going to pose today to all of us is there an alternative way of reaping the benefits of learning to improve policies for navigation? And I guess the answer is yes. Why else would I be asking you this question? We can get quite far simply by watching egocentric videos of people walking around in their own environment. Okay, so let me tell you, let's go in and see how we can actually go about doing this by just watching videos. But before I tell you what we do, I think I should tell you what kind of videos I'm talking about. So I'm referring to these videos you can find on YouTube, which are essentially real estate video tours, right? So there's someone who's trying to rent out their apartment or their house, and then they, record this kind of a video, and then they upload it to YouTube, and you can basically, there's data of this form that is available, right? Now, there's not just one video. I mean, it turns out you can actually try to find these, and you can find quite a few. And in fact, with the paper that I'm going to present, we collected a data set of this, and this is all, you can also take a look at these and so forth, right? Okay. So what do such videos tell us about how we can navigate, right? So let's go back to the examples that I was working with. The first place where videos can help us navigate is that they can actually show us where you can go from here and how, right? So I showed you this picture. Now, in this video, if there was a recording of someone walking out of this room and turning to the left, that actually tells you that at this location, in this particular scene, you can actually go out and turn left. That's a feasible trajectory, right? So watching videos tells us about what is behind obstacles, if you will, right? That's number one. Number two, what they tell us is what is next to what, right? So again, in this particular snippet, if you go forward, I mean, I'm going to just play this video forward. I mean, this video is going to show us that there is going to be a couch, right? Now, you can use this kind of a video snippet to actually infer that if you are seeing this kind of a television right in front of you, then it is likely that a couch could be facing this television, right? So you know that televisions and couches co-occur. If you're just looking at a television, now you can actually infer something about where can couches be, right? So that's kind of the basic idea of how we can use videos for learning these kind of cues for navigation. And I'm going to start with talking about the latter part first. And if time permits, I'll talk about the former. We'll see. Right. Yeah, so this was some work that we presented at NeurIPS last year and was led by my students Matthew Chang and Arjun Gupta. And basically, yeah, we were working with these videos and we were trying to learn navigation policy. Right? Now, there are some challenges that come about when we are trying to use these kind of videos for doing learning, right? And there is a video that we've been looking at. Now, these videos don't come with action labels. I don't know what is the action that the person who is recording this video is taking between one frame and another frame, right? So that's kind of problem number one. Problem number two is I actually don't know what is the goal of this particular agent, right? I don't know what is this person going to show me next, where is this person going to go, and so forth. So I don't know these aspects. And third, the trajectory that this person is taking may actually not be optimal, right? So what you saw in this video so far is this person went in and took like a detour into a bathroom and then came out and so forth, right? So the trajectory is actually, the trajectories that have been showcased over here are not optimal. And that poses learning challenges when we're trying to learn something. So what we did in this work was try to address these challenges. And the way we do this is that videos don't come with action labels. We are going to do action grounding via inverse model, and I'll tell you more about that. I don't know what is the goal and the intent of the person who is doing this. I can run off-the-shelf object detectors to label frames with desired objects or with desired goals, right? And trajectories may not be optimal, but I can use Q-learning, which can allow me to learn optimal behavior even from suboptimal data. Right? Okay, so let's look at these aspects in more detail. So I mentioned this thing called an inverse model. What is an inverse model? Basically, you can build an inverse model as simply as you take a robot and you let it interact with the world, right? You just let it execute random actions. It collects image of this data of this form, IT, action 80, image IT plus 1, and so forth. Now, from this data, you can actually train an inverse model, which looks at the two frames and tries to predict what action did the robot take in between those two frames. Okay? And this is a reasonably simple short horizon model, right? You only need to look at a couple of frames in order to make a prediction for what you want, what action you took, right? So this can be learned in a sample efficient manner, right? So, I mean, you don't need very many samples, right? So, and there's a small amount of interaction data you can collect and then you can build this inverse model. If you're working specifically in the case of navigation, you can actually also use structure from motion. And that will also give you a sense of, did you go forward? Did you turn left? Did you turn right? And again, structure from motion on short sequences will very likely almost always work, right? On long sequences, you have issues with loop closure and so forth. But I think on short sequences, it will work. And that's, we've tried it. It is sufficient for what we want to do, right? Okay, so that's aspect number one. Aspect number two that I mentioned on the previous slide was Q-learning. And again, if you're not familiar with Q-learning, unfortunately, I won't be able to go into all the details of Q-learning, but I'll give you a brief overview. It's a technique to estimate Q values, Q star of S, A in a Markov decision process from off-policy data. And this data, you can think of this in the form of transition quadruples. So you are in some state, you take some action, you get to a new state and you get some reward. And this is called a transition quadruple. And Q-learning takes like a database of these quadruples, and it can basically learn optimal Q functions from there, right? And what is a Q function? It is essentially the expected return of an optimal policy when executing action A from state S. Or colloquially, you can say how close you are to the goal after you've executed action A, right? So that's kind of what Q star of S, A captures. And as I said, the result is even from suboptimal data, you can still estimate the value of the optimal policy through Q-learning. And I mean, there are some mild technical conditions that under which you can do this, but that's kind of what Q-learning is, right? So we can put all of this together to come up with this framework that we are calling value learning from videos. And this framework consists of, as I said, we're going to work with real estate videos from YouTube, right? So this is a video fragment, if you will. We run this inverse model to do action grounding. This inverse model has been trained on a small amount of interaction data. So we are now being able to label what action did I take, or what action would the agent take in order to go from one frame to another frame, right? So that's kind of what these actions are. We can do goal labeling by running an object detector. So we take this frame and we run an COCO-based detector, and then we get, we can label it with rewards, right? So if a bed detector fires, I know that there is a bed over here and I can get that. And now you can take these 4 pieces and you can form Q-learning quadruples. And once you have done this, you can actually do Q-learning on these quadruples and you get a value function back. And this value function f of I, c. So this function takes in an image and a category of object that you are trying to look for, right? So in this case, we are working with this problem of finding objects in scenes, and C is basically let's say a categorical label for what category you are trying to look for. So you can do this learning, and then you basically get this function fi, c, which is a value function that basically learns implicitly how close are you to an object of category C from the image ID, right? Okay, right. So we can actually see what does this function learn. So here is a panorama that we're going to run this function on. And I'm showing you predictions for different categories that we trained this model for. And what we can note is that this value is high for these categories: chair, couches, and dining tables in the left side of this image. And I mean, this is not surprising. You can quite already see a couch. If there's a couch, perhaps there's a dining table. In fact, you can actually see a dining table in the far back over here. But if there's a couch, perhaps there's going to be a chair over there and so forth, right? So it's actually pretty high in this region and also in this region where you can see couches. But more interestingly, this value function is also high along this hallway for categories bed and toilet, right? Now, you're not seeing a bed in this image anywhere, but this model is able to learn that if I go down a hallway, it is possible that there's going to be a bedroom somewhere down the hallway and it can get there, right? So this is essentially this predictive nature of what can you do in a scene that we wanted to capture, and value functions learned in this manner are actually able to capture this detail, right? You can actually look at this on top of a map. There is a dining table over here. I'm visualizing the value function for nearness to a dining table, and you can see that this value function bleeds smoothly as you're going away from a dining table, right? And this is exactly what we wanted to capture. Okay, good. Now, once we have learned these value functions, the next obvious question is how can we actually use these value functions for anything, right? And that's kind of how we are going to do this. Is we are going to use these in conjunction with a hierarchical policy. This hierarchical policy consists of a high-level policy and a low-level policy. The high-level policy decides where to go and emits a short-term goal, and the low-level policy takes in the short-term goal and tries to get there, right? The high-level policy is going to build a topological map of the environment, and this is based on some of our past work that was presented at actually this workshop last year and also at the conference. And this basically is building a graph-based representation of space. There are past nodes, there is a current node, and you're maintaining a frontier of predictions, a frontier of directions in which you can go, right? And you can get this easily from a depth camera if you have one on your robot. And we're also keeping track of these value predictions that I described to you, which is essentially measuring what directions are promising to get to a particular category of interest. So that's kind of what you're seeing with these blue dots. And at each step, what we do is we essentially sample the most promising direction, compute the delta pose, and try to basically ask the low-level policy to get there, right? This low-level policy, again, we are using some classical tools over here, which is essentially we are using fast marching method for path planning, right? Locally, you can do this, ego motion errors, etc., not as much of a problem and so forth, right? And this process can basically repeat and go on from there, right? Okay, good. I mean, here are some results. So this is, again, as I said, for this object goal task, we are measuring SPL, which is how efficiently are you able to get there. And here are some different methods. So on the red star is basically our method, which has been trained on YouTube videos. It does pretty well. I mean, I guess if I'm showing you the spot. We are comparing against RL-based methods, which are these lines, which take a lot of interaction samples for training, but are actually quite far from the performance that our policy is able to get. I'm also plotting here, interestingly enough, a classical baseline, which is called detection seeker, which does a very simple thing, which is if it randomly explores the environment, and if it sees an object, it tries to go there. And it turns out this actually works much better than the RL methods that we tried. And this is, again, I think, why I wanted to say you should always ask the question, what are your RL methods learning, right? And are they able to convincingly outperform a classical baseline and so forth, right? So it turns out, I mean, comparisons are in our favor. We are actually able to do better. We are able to learn something on top of classical baselines, and we're able to do that in a very sample efficient manner, much more so than RL-based methods, right? We have actually also done some ablations, which in interest of time, I guess I won't quite be able to go into, but I encourage you to read the paper for more details over here. Here are some policies that we are showing results for. This is basically, you're trying to find dining tables and so forth in this particular example, and couches and so forth, and it's able to do that successfully. Okay, so I think that's kind of one aspect that I mentioned to you about, which is how can we use videos for finding out what is next to what, right? And how we can actually operationalize this intuition that I gave you in the very beginning in order to build a computation system for doing this. It turns out we have actually also done some work on where can you go from here and how, but in interest of time, I won't quite go into that. This is basically this paper that appeared at Coral in 2019. And I encourage you to, I'm going to skip over this, but basically the story is the same. You basically have very similar challenges. You don't know what the person is going to do. You can do multiple things from each location in the scene. So how do you learn something which can actually learn from that kind of data? And I would encourage you to look at this Coral paper for details on that. Right? Okay, so I think that was the learning to move part, which where basically I told you about how can we learn policies for moving around without too much direct interaction by leveraging videos that could be found, for example, on YouTube. In the remaining 5 minutes or so, I'll basically talk about how can we move in order to learn, right? Right. So again, I'll first give you some intuition. Let's say you're trying to do object detection, right? And you have downloaded a detector trained on the Microsoft Coco dataset, and you run it on the image that you're seeing on the left-hand side. It kind of sees this chair in the far back, not quite sure whether it is a chair or not, right? Now, if this were a robot, if this were an image on the internet, you have no other option but to ask a human for a label. But if this is a robot that can actually walk around in this environment, this robot can actually walk towards this chair. And at some point, the chair detector that it has downloaded from the internet will actually say that this is a chair. And now you can actually go back in time and you can actually label instances that, okay, these were also chairs and so forth, right? So the two key questions that end up arising over here is how to seek data that provides opportunities for such learning, and how do we improve our models based on this data, right? And these are a couple of questions that we looked at in a recent paper called SEAL, which is self-supervised embodied active learning, where essentially we are doing everything with self-supervision. We're not asking anyone else for labels. We have a model. We are just observing the world, and we are using the predictions of this model to improve the model itself. We are doing this in an embodied context. So this agent can actually interact with the world around it in order to gather the data and so forth. And it does so in an active manner. It decides how to interact with the world in order to improve the model, right? And the answers to these two questions are, we have something which we are calling gainful curiosity for determining what data to seek. And we are going to be doing label propagation in 3D semantic maps in order to improve the model that we have. Right? So at the heart of basically this method is this function for 3D semantic mapping, where essentially you are getting RGBD images, and basically you are building a 3D semantic map of the world by running your mask RCNN that gives you some predictions. The depth image gives you basically geometry of the world, and you can string this together in the form of a 3D semantic map. And basically you have that. Once you have the 3D semantic map, yeah, so this is what 3D semantic mapping looks like. You have RGB images, you're running mask RCNN, and you're incrementally building this map continuously as you go. And once you have this map, now you can actually do gainful curiosity on top of this, right? Where basically what we are doing is we aggregate, once the agent has built up a map, we can actually compute a reward for this agent by counting how many voxels did we have such that the score is more than 0.9, right? So I have at least one confident detection in some sense. That's kind of what I'm trying to capture here. And this is going to generate a reward, and that reward is what I'm going to use to learn an exploration policy, right? So this basically answers this question: how should I move around in the world in order to create opportunities for learning how to improve my model? So that's kind of one aspect of this. The second aspect of this is 3D label propagation, where basically once you have built this map, you can do 3D label propagation, and you can render out labels for images that you have seen, right? And basically you render out this reconstruction that you have, and that gives you where are the different objects in the world. On the top, I'm showing you these labels after they have been propagated, and on the bottom, I'm showing you labels by just running mask RCNN that you have, right? And as you notice, mask RCN will have false negatives, which our label smoothing doesn't have. If you go further along in this trajectory, you will also see false positives, which is, again, errors that we are able to clean up, right? And now, basically, you have good labels. And now what you can do is you can basically train a perception model, which will right? You can fine tune your perception model that you have. Right? And this actually, just doing this process actually leads to improvements in performance. So a pre-trained mask RCNN model on this kind of data, egocentric data of this form, gives you 34.8 mean average precision. I guess we are doing label propagation. There are other ways in which you can do label propagation. We are learning exploration policy. There are other ways in which you can learn an exploration policy. And it turns out what we are doing improves performance, both in terms of label propagation and exploration policy. And we're able to get like a 5% improvement in performance over pre-trained mask RCNN in this fashion. Right? You can also look at segmentation metrics. There is also an improvement over there. Okay, so I think that's kind of what the two parts that I wanted to talk about. I showed you how we can learn to move, where we are using egocentric videos to learn policies for navigation. And I also showed you how we can move to learn, which is I presented this framework on self-supervised embodied active learning. And I want to thank my funders, and here are links to papers and all the students who basically did all the work over here that I talked about. Yeah, thank you, and I'm happy to take questions in the remaining few minutes.
Yeah, thank you. Thank you for a nice talk. So yeah, there's a few questions. So one question from by Yan Zhang. He's asking that path and motion planning could also solve this problem and would not suffer from train test domain gap. So what is the key advantage of the learning-based method in your opinion?
Yeah, that's actually a very good question. And I think in some sense, path and motion planning are working after perception has been done, right? And if you notice, what we are tackling in our work is essentially how can we improve perception, right? We are basically pointing at bottlenecks in perception rather than in motion planning, in path and motion planning. In fact, under the hood, we are actually using path and motion planning, but we are using it with more predictive representations of the world that we have learned. Right? So I guess I hope that answers your question.
Yeah, thanks. And also, yeah, there's also another question. Yeah, so from Xiaolong Li, he's asking, he's wondering for the goal objects in learning to move tasks, do we also want to use small objects like a pillow, scissor, knife, etc.? Here it seems that we only target at large objects like desks or beds.
That's a very good question. And by all means, I think in fact, for smaller objects, these semantic cues will be even more powerful, right? So if you're looking for a pillow, I mean, very likely it's going to be in a bedroom, right? Whereas a chair could actually be pretty much in anywhere, right? So I think, or scissors, it might very likely be in some cupboard on a table or something. So it's a very good question. And I think this gets to the very heart of what I was saying in the very beginning, which is if all you want to learn is these contextual priors, do you really need end-to-end RL for doing that? Or can you sidestep that and learn that in any other fashion? Right. So I think, I mean, your question is a very good one. I hope that answers.
Yeah. Okay. Got it. Yeah. Thank you. Thank you for your reply. Yeah. So I think for if you have any more questions, you can also post it in the chat box. And also, Sarah, if you have time, feel free to kind of stay in the chat box and reply to them. Yeah. Just take your time. Yeah. Also, thank you for coming. Yeah. Okay.